Oh, one thing about example 1 that I just wanted to go back and point out is the textbook asked example 1 this way, but on a test, you might have got this same question and it would have just looked like this. Graph y equals negative 1/4 absolute value of x. That's the same question, but now you have to know that absolute value of x is the red graph. And you would have to be able to pull off the points off a red graph from your memory, and then notice that the negative in the 1/4 was outside of the function, and do exactly the same question. It's just written in a different way.
Why are the last two coordinates for the blue graph on?
Because when I said I checked over things, I didn't do a good enough job. They're not supposed to be positive. They are supposed to be negative. And I would love to say that I did exactly the same thing that I warned you that you will do. Well, no, I did exactly. I started thinking ahead about what I was going to do next. And even though I knew that there was negatives because I graphed them in the right spot, I was already thinking about the next thing. We do this especially when math is what we think is easy math, right? Do you know what the #1 mistake, simple mental math mistake that grade 12 students do? You wouldn't believe how many times students write 1 times 1 equals 2. And the reason is it's so easy. 1 times 1 and 1 plus 1 are so easy you don't have to think about them. And because they're so easy and you don't have to think about them, you sometimes don't think about them and do the other one instead of, like you add instead of multiply, or multiply instead of add. And it's when we're doing our easiest things that we decide not to pay attention, and that's usually where the most mistakes happen. They find that most people get into the most stupid car accidents the closest to their house, because they've driven that area so many times that they don't think about it anymore. And they're like, this is easy. And they're like, oh, I didn't realize it was slippery. And I drove into the snowbank. Okay, so example 2. And please, every time you notice that I make a little mistake like that, point it out. Because somebody else is like really confused and they're like, is it supposed to be like that? No, I will be making little mistakes like that, not on purpose. So here's the graph of g of x. We see this 0.5. We can think about it as a fraction as well. That might be easier. This is going to be inside the function, so it's horizontal. Will it be a stretch or a compression? We will call this a stretch because we are multiplying by something bigger than 1. It's a horizontal stretch because we're going to multiply our x values by 2. If we draw our arrow diagram this time, let's label these 4 key points. We have -3, 2, -1, 5, 3, 3, and 4, -2. Draw our arrow diagram. Now above the arrow, the only thing we have to do is multiply our x coordinates by 2. That means our y coordinates are not going to change. And when we multiply our x coordinates by 2, we'll get -6, -2, +6, and 8. We can take those points and label them. -6, 2, -1, 2, 5, 6, 3, and 8, -2. Connect the lines. one both, just so you can see both. Smallest x value, -6. Biggest x value, +8 for the blue one. If you wrote this in set notation, your x would be between -6 and 8. The range for the blue one, smallest y value, -2. Biggest y value, +5. In set notation, it would be between -2 and 5. For the red one, I'll just do one notation. Smallest x value, -3. Biggest x value, 4. Smallest y value, -2. Biggest y value, 5. And questions for practice on this one? 4 and 8.